Okay, thanks, Roland. Um, so I'll get started. Again, apologies for not being able to make it there. I'm disappointed I can't be there and get to catch up with a lot of you. But hopefully I'll get up there again soon. So in this talk, I'm going to present some results where we've applied a new image correlation technique to try and measure the stresses and friction along the faults that ruptured during the 2019 Ridgecrest earthquake sequence, and I'll make the argument that we can use these satellite images to measure these important geomechanical properties. Okay, so the first part of the talk, I'll kind of give a brief overview of this new optical image pixel tracking technique. This is an approach, if you're not familiar with it, that can measure the horizontal and now the vertical component of surface motion. And so this is kind of a useful toolkit. It can be applied to a number of problems, including measuring surface motion associated with sand dune migration, glaciers, landslides, and of course earthquakes, which is what I'm going to be talking about. This is kind of a very simple schematic showing how pixel tracking works. Essentially, typically you'd have an image before and after some event, and you would apply some correlation scheme. So usually you'd have some kind of correlation window that tries to track the lateral shift in features between one image to the next. And from that lateral translation, you would get the subpixel, the motion to subpixel precision in the east to west and north south direction. So this is kind of a simple example of the traditional image correlation approach. And so you can see how this could be applied to other kinds of geological processes. So the second part of the talk, which is what I'll mostly focus on, is how we've applied this new approach to try and measure the stress orientations, the absolute magnitude of stresses, and the fault friction that occurred during the 2019 Ridgecrest earthquake sequence. So just a quick overview of the image correlation approach. So the standard traditional methods would give you an estimate of the horizontal component of motion. So this is an example here for the Kaikoura earthquake in New Zealand, where you can see this side of the fault moving back and forth. These are Sentinel-2 satellite images. These are optical data, so we're not using radar, we're using the optical part of the electromagnetic spectrum, the visible part. And so the new approach that we have now is, instead of correlating just a pair of images before and after an earthquake, what you now need are two pairs. So one pair of images before the earthquake and another pair of images after the earthquake. And the reason why is that if those two images are taken in slightly different look directions, as shown here, you can then triangulate the 3D position of each pixel and then track its 3D change with time and get the full 3D surface displacement. So this is showing a satellite time one, another satellite taking an image before the earthquake. These lines show the look directions. And so what we do is using a ray tracing approach to calculate the intersection location of these two look directions. So this requires us to know the satellite position, the attitude, the velocity, the look direction. And it requires us to have this before and after the earthquake. So this is, you need a minimum of at least 4 images. And so this automated approach then allows us to triangulate the position of pixels before and after an event to calculate 3D surface motion. And then we implemented an ICA filtering technique to help try and remove geometrical artifacts that can be associated with images. So this technique is also useful because we've adapted it now to handle different types of satellite platforms. So we can use images from Spot or Worldview, different image acquisitions. And so this is useful because it then allows us to have a greater range or diversity in look direction orientations. And so we can get a better, more precise estimate of the 3D position of each pixel. So this is a workflow schematic of the traditional image correlation approach that would get you the surface displacement in 2D. And if you can build DMs before and after an earthquake, you could get the 3D. And then this is now our new workflow. I won't go into the details, but the main kind of advancements we've made is improving or optimizing the what's called the rigorous tensor model. And so we basically try to improve the constraint of the satellite position, the attitude where it's looking, and its velocity. And this allows us to better refine the orthorectification, and so we can try and better correct for the some geometrical effects, which previously could be a large source of noise. The second step is on the ray tracing approach I talked about, and then lastly we added this kind of post-processing independent component analysis to the workflow. And so this workflow is kind of outlined in the study. You can scan this QR code if you're interested, and you can also now download the new Coseismic Plus from this GitHub repository. So that's now open. So this is a quick overview, just showing the comparison of a surface motion in the east-west direction for the 1999 Izmit earthquake. So you can see in the top, this is a result from the traditional approach. On the bottom, we then have the result using our new 3D method for spot 2 images. So you can see here in the result using the traditional method, we have these large topographic artifacts. We have these sensor array artifacts. You see these kind of stripes, which are artifacts of the CCD arrays in the image. And when this new technique, we can remove these effectively because we're improving the rigorous sensor model calculation estimate. And we're also able to remove these sensor array artifacts through this ICA filtering. And so we draw profiles across the fault rupture here. This is the fault rupture. We get a much more a cleaner estimate of the total fault offset. So the red line is the surface motion associated with this from this original noisier result, and the blue is our new result here. As you can see, we can get a much better constraint of what the total offset is across the fault, which is about 4 meters in this case. So that's given by the differential motion across the two sides of the fault here, along this profile from A to B. Okay, so we've now applied. So what we're going to do now is apply this.
Can I ask a quick question, Chris?
Sure.
What are the requirements in terms of separation of the satellite? This presumably doesn't work if the satellite is passing by too close or too far.
In terms of like the spatial baseline.
Well, in INSA, right, the spatial baseline, right? In INSA, we have certain requirements for the perpendicular baseline. I assume something similar applies here.
Right. So really, yeah, you want a graded range in the look orientation. So our images typically span about 20-30 degrees difference in the look directions. Yeah, and so if you can improve upon that, you'll have a more accurate estimate of the vertical component of motion. If you can get a great, if you don't have a large diversity in a large range in the look direction, you won't have a very precise estimate on the vertical component of motion. So you can still get the 2D component, just the vertical won't be as accurate.
Cool.
Yeah.
Does this method also require the authentication before you?
Yeah.
Okay.
Yeah, it does.
Okay.
Yeah, exactly. Yeah, I'll show a result after this that kind of relates to that question. So yeah, here's the data sets we use for the Ridgecrest event. So here we're using a mix of satellites. We have worldview 1, 2, and 3. We're using just over 200 images in total for this event. And we also have spot 6, and then our reference images are high resolution aerial images. And this shows the kind of time span of when these different images were acquired. So here's the earthquake, and we have images going back more than a few years before the event. Luckily, this is a desert environment, it's stable, so you can use images going further back because the surface doesn't change too much. So this is here where we are correlating images between the various pairs. That's shown by the columns, and the rows are showing the different DMs we use. So we tested how does a DM affect the orthorectification and the quality of the results. So you can see with SRTM DM, which is very coarse, you get a worse result compared to a DM built from the images themselves. And so this is correlating images just before the earthquake.
What's that, Oliver?
What's DEM?
DEM, digital elevation model. Yeah, topography.
Sorry, yeah, digital elevation model, yeah. So this is a correlation between two images taken before the earthquake, so there's no tectonic signal, and these are correlations between images taken before and after the earthquake. So you can see the tectonic signal here. And so what we've done so one important feature is that in our ray tracing step is that when you're calculating the intersection of those look vectors, is that due to the inaccuracies in the digital elevation models, that causes an apparent motion or displacement, and so that's induced by this parallax effect that's not accounted for in the DMs. And so because we're solving for that in the ray tracing step, you can effectively remove that bias imposed by the inaccuracy in the digital elevation model. And so it means that this new approach means that the orthorectification is largely insensitive to the type of DM that you use. And then lastly, this is showing the ICA filtering result, whereas this is basically comparing the different independent component sources for our results. So ICA is a statistical technique which basically decomposes your data into statistically independent sources. So this source S1 shows us the tectonic signal. That's because this signal is global or can be found in all of the images. But we go to lower or higher order components, we can start to see these smaller scale signals, and these ones are related to the satellite jitter, this kind of cross striping, and the vertical striping is the CCD array artifacts. This is ICA shows how it can help separate the tectonic signal from the geometrical artifacts. And this is an example of the result for one of the images for Ridgecrest. This is the east-west, the north-south, and vertical component of motion. This is the surface rupture here. The red line is the error distribution for a far-field stable region using the traditional approach for each component of motion. And then the blue is our distribution. And you can see we have a much tighter distribution, and we don't have this bimodal distribution because we're removing those geometrical artifacts. So we can reduce the noise by about a factor of 2.5 or almost 3. So again, here's the final result for Ridgecrest using this approach. This is the east-west component of motion, the vertical, and then the north-south component of motion. This is the main shock rupture here, and then this is the foreshock rupture right here. So one of the things you can do with these deformation maps is compute strain. So from these 3D deformation maps, you can calculate the 2D displacement gradients, because we don't have the constraint of how displacement varies with depth, so we can't compute 3D strains, but you can get the 2D strain tensor. So you compute finite strains here because we're dealing with large finite strains across the rupture, and then we can also calculate the finite dilatation. And so this is useful because it can give you an idea of the intensity and the width of the deformation zone, or the amount of fault extension and compression. So here's a quick example of this.
Chris, can I ask a question on that? So on that slide, there was a label called predicted. Is that what's that? What does that mean? The predicted, yeah, observed, predicted. What's the model?
Oh, sorry. This relates later to the talk. This is gonna go into the stress model, and these are our slip vectors that we measure along the rupture. Okay. Yeah, this will make more sense later. But the main point to take away from this is just the surface deformation maps we get from this image correlation approach. Okay. Yeah. Thanks. So here in this slide, I'm showing the horizontal component of motion. You can see along this part of the rupture, these surface motion vectors are moving in opposite directions. So you can see this part of the rupture is the strike slip, and then here this bend, the surface motion vectors are moving away from each other. So this is a region of transtension, and also subsidence here. This part of the fault is subsiding, and so you can put the dilatational strain. This region is undergoing transtension or positive dilatation extension, and here you can see the variation dilatation from transpression to transtension as due to this kind of subtle curvature of the fault. And again, we can see something similar here along this right bend, where we have these surface motion vectors moving away from each other. this region of subsidence, and then positive dilatation due to extensional strain.
What's the difference between the top and the bottom?
Oh, they're just different step over bends along the Ridgecrest rupture. So these are maybe about a few kilometers away from each other. Yeah, so we can from these strain or deformation maps, you can also calculate the total fault offset. This is just showing the amount of fault offset in the parallel direction, the perpendicular, and the vertical component of motion. And from that, because you get these three components, we can calculate the slip vector. And we can get the slip magnitudes. Here, this is indicating a rake of about -108 and a fault dip of about 54 degrees along here. So this is kind of consistent with a transtensional kind of oblique strike slip normal fault motion. And so, there's a few things we can do with these deformation maps. You can do the fault offset and the magnitude width of distributed strain, or like for regions of transtension and transpression. But one of the things I want to focus in this talk is the variation of slip on the rupture associated with a pretty prominent fault bend. So here's the slip distribution for the Ridgecrest earthquake along the mainshock along here. So this is south to north. The blue is the parallel component of fault motion. You can see there's a significant decrease in slip right here, and that's associated with this bend right here. It's about 19 degrees change in orientation right here. This is where this slip decrease occurs. And so what we want to try and do with this data set is try and answer some of these specific questions, which is how heterogeneous are stresses along a fault system. Can we try and use them to say something about the absolute stresses in the crust, and how strong are faults and how much do they dynamically weaken? And so the idea here is to use these 3D slip vectors to constrain the stress state, the initial stresses, and then the fault friction. So I'm going to talk about how we do that. First of all, we just want to quickly go over, why are we interested in stresses and friction? How does it affect earthquake rupture? So this is a really nice figure from Jan Hoxton showing the heterogeneity of the SH max direction in Southern California. So SH max is the direction of maximum horizontal compressive stress. And so constraining the orientation of stress is important because it gives us an idea of the style of faulting to expect. The magnitude of stresses is important because it can affect the size and recurrence of earthquakes and the extent of surface topography. And typically, this is measured either using focal mechanisms, so you can invert focal mechanisms for the stress orientation. I'll talk a little bit more about how that's done using borehole breakouts or conjugate fault orientations. And then the fault friction, typically how this is observed, and the evolution of fault friction is how it varies with slip. So this is showing the evolution of friction with slip. Here we have some friction with some initial value, and then we have an increase towards the static friction or the yielding friction, and then that decreases typically to a steady state value, which is the dynamic friction. And that typically occurs at a slip amount called d sub c, which is the critical slip distance. Okay. And so fault friction obviously is important for understanding how strong faults are, what's the amount of stress that the faults can resist, the extent of the stress drop, the amount of radiated energy, and it can also affect the amount of fault slip too. So here in this talk, the main approach we take to try and constrain friction is that we try and understand how the initial stresses change with the fault orientation, given the ambient stress field. And we try and understand how those initial stresses affect the stress drop and the magnitude of slip. And I'll talk about a little bit how we do that. So here's that same diagram I had before. And here's a fault surface inclined at some angle to sigma 1, which is the maximum compressive stress. And so here we have the stress drop is the difference between that initial shear stress and the dynamic shear stress. This is dynamic friction and the normal stress. And so you can see if you compare this fault surface to this fault surface is a bit better inclined or better oriented to the stress field. It has a higher initial it'll have a higher initial stress, or a higher initial shear stress and friction. So the frictional amount will decrease by a larger amount, and we expect a larger amount of slip here compared to a fault surface that has is more poorly oriented to the stress field and has a lower initial shear stress. So this fault would have a higher initial shear stress, and therefore expect a larger amount of stress drop. So the idea is that with this simple equation here by Aki et al., so D is the amount of the displacement along the fault, W is the seismogenic width, C is a geometrical factor, G is a shear modulus, and delta tau is the stress drop. We would expect the amount of slip to scale with the amount of stress drop. And so the idea is that faults that are more well aligned to the stress field will have a higher initial stress, larger stress drop, and a larger amount of slip, while compared to more poorly oriented faults will have a lower initial stress, a lower stress drop, and a lower total displacement. And so this is how we try and relate the slip magnitude to the stress drop here and the initial stresses.
And Chris, geometrical factor is just another thing related to the shape of the slip patch?
Yeah,
Exactly.
It's related to the shape. So for Ridgecrest is about 0.56, and it's a function of the length and the width of the rupture.
Oh, I see. Mm-hmm.
Yeah. And so one of the key assumptions here is that this is a purely quasi-static analysis, so we're not accounted for dynamic effects. And then we also assume that the dynamic friction drops to some steady state value. And this is assuming that sufficient slidings occur. We've kind of exceeded this D sub C value. And for Ridgecrest, we think this, a reasonable assumption. This is typically what's seen in the lab.
Chris,
Yeah.
just to clarify, for the previous equation that you showed from Aki, that's like this geometric factor and everything, this would be for the average stress drop and average slip, right? Not necessarily,
Right.
Like, is the assumption here that you have a uniform stress drop within, or like presumably this will be the average?
Yeah, so we assume the W, C, and G are an average of the region we look at, but we allow variability for the stress drop for particular fault planes. And this is what we relate to variations in displacement. So I'll go a little bit about I'll talk a little about how we do that. So does that answer your question?
Yeah.
Okay, I can move on because I'll kind of get back to it in a second, but in a few more slides. Okay, so there's been some previous theoretical work looking at the effect of fault bends on the initial stresses and friction. So there's an example by Case and Day where they use a theoretical dynamic model to look at the effect of a fault bend or kink on the propagation of rupture along this fault. And so they found that these geometrical changes in the fault geometry that can affect the initial stresses and are important and actually can affect are quite important for affecting the final slip distribution. So this example here where we have a slip distribution for a fault with depth, and along the fault and contours for the amount of slip. This is with a no bend case. It's just a purely straight fault. And then if they introduce a bend right here, where theta is the bend angle, so theta is right here, it can start to suppress slip. And as they make the bend angle more severe, it can start to almost completely suppress propagation. And so this is largely because as you change the bend angle shown here and with theta with minus or releasing a restraining bend, you're changing the initial shear stress, you're increasing that static friction and the dynamic friction. So the effect of this bend is as you increase that bend, it's starting to suppress, lower the shear stresses and increase the dynamic and static friction, and so that suppresses slip as we go to higher bend angles. And so the idea is that even though this dynamic model, this is a fully dynamic model here, we want to try and understand using a quasi-static approach in this study, if we can find a kind of similar observable effect on the Ridgecrest earthquake. So here we first need the initial stress to do this. So what we do to get the initial stresses is we take those slip vectors that we measure from the deformation maps and we invert them for the stress state. And so we do that following the Wallace-Bock criterion. This is kind of a standard approach in seismology to estimate the stresses using focal mechanisms. So this is an example here where I'm varying the stress orientation, and this is showing the range of slip vectors along different faults. And so the idea is that if you can measure the slip vectors in a range of faults of different orientations, you can then constrain the stress state that caused the observed slip motion. And the main assumption here is that the shear stress occurs in the parallel direction to the slip direction on these faults. So this is our inversion approach. We use a damped L1 regression, so we try and suppress or penalize spatial gradients in the stress tensor along the rupture. And so this approach gives us the deviatoric stresses. We don't get the absolute magnitudes, but we do get an estimate of the R shape ratio value, which gives you an idea of the relative magnitude of stresses, or the shape of the stress tensor. Okay, and so back to these deformation maps.
So Chris,
yeah.
Is that similar to the estimate of the stress using the focal mechanism solutions?
Yeah, it's the same idea.
Okay.
But instead of focal mechanisms, we're using slip vectors.
Seismic, yeah, right.
Yeah, which goes back to your original question about what that was showing on the deformation maps.
Right. Thank you.
Yeah. So here on the rupture, we take those profiles along all the fractures we can observe. We come up with about 240 slip vector measurements about every 150 meters along the rupture. So this is showing the rake of the slip vector. You can hear we have lateral slip, mostly right lateral slip, and then some transtensional oblique strikes at normal slip in this area. And then just showing the slip magnitude here, and showing the variation along strike. So we use these slip vectors to invert for the stress state. And we break up the rupture into 3 different zones from north to south along the rupture. So you have a zone in the south, the central zone, and the north zone. And so this is showing our stress tensor results for just the south zone here. So if you concentrate on this figure here, this shows the stress orientations. The colors show our confidence intervals for the different principal stresses. So you can see here, in this zone, sigma 1, which is kind of this red, shown by this red color, is almost exactly north-south. Sigma 2 is almost exactly vertical. So this is kind of a classical Andersonian type strike-slip stress regime. The other symbols here are the stress orientations from other studies, either using the background seismicity or aftershocks. And so you can see a pretty good close agreement between some of these. And so again, if you move up to the central zone, we see a similar result, where a close agreement between our stress orientations and those from background studies, other studies. And then again, in the north, we have sigma 1 direction, which is actually now rotated quite a bit towards the east. So one feature that we find is that the stress direction seems to rotate from south to north on the rupture by about 12 degrees. Now, the second thing to take note is that the R shape, that shape ratio value, seems to decrease too from south to north along the rupture. So it becomes more transtensional as you go south to north along the rupture. That R value decreases. That's also in a good agreement with a value from Harderbach found. So the vertical bars show her result. And the colors here in this diagram, I won't go into detail what this shows, but this is basically illustrating the kind of misfit between our observed slip vector directions in black and the gray, which is the predicted from our stress model. So you can see there's fairly good agreement between those two. Another way of kind of showing the misfit of our stress model is comparing the observed slip vectors to those predicted along different parts of the rupture. We find a fairly good fit with a mean angular misfit about 4 degrees or 96% variance reduction. So there's three different zones seem to be explain well the orientations of the slip direction at different points on the rupture. So now I want to try and visualize our stress state in Mohr space. So if you're unfamiliar with Mohr circles or these types of diagrams, I'll quickly go through it. So this axis is showing the normal stress, and this axis is showing the shear stress. So the sign convention we have is that positive normal stresses are compressive and positive shear stresses are right laterals. Okay, and so what we can do is we can visualize the stress tensor we came up with in the central zone. And that's what's plotted here. This is our stress tensor. And so it's a really useful way to show how not just the stress tensor is kind of organized, but how what are the normal and shear stresses projected on a certain fault surface. So for example, here we have a fault surface inclined at some angle from sigma 1. It has this normal stress and this shear stress. And if you have a look at another fault that's way over here, it's more poorly aligned to the stress field. You can see there's a larger angle between sigma 1, the fault phi naught is larger. And so you get a larger normal stress, because this fault is more poorly oriented and a slightly different shear stress. Okay, and so one important thing to keep in mind is that with the stress tensor, we don't have the absolute magnitude of the stress tensor at this point. We don't know the radius of this circle. We don't know where sigma 1, 2, and 3 are located in absolute stress space. So these points show the principal stresses where the shear stresses are 0. So we don't know where we are in Mohr space, or we don't know the size of this Mohr circle at the moment. But one thing we can do to try and get the radius of that Mohr circle is by measuring the stress rotations. So what we can do is compare the orientation of the stresses that we estimate with those from aftershocks. And so the idea is that if the stress drop of the main shock event is fairly large compared to the deviatoric stresses in the crust, that stress drop will perturb the stress field and will induce a rotation. And if you can measure that rotation and you make an assumption about the stress drop, you can then calculate the delta sigma, the maximum shear stress or the deviatoric stress magnitude. And that's the radius of a Mohr circle. So that's what we do. We compare our stress orientation to those derived from aftershocks. These are the values we get. So this is the equation we use as kind of the classical approach by Harderbach and Hodgson. So delta sigma is the value we're trying to constrain. Delta theta is the amount of stress rotation, which is about 5 to 10 degrees in some places. Theta is the SH max direction with the angle of SH max with our fault trace, which we know because we know the fault orientation, we have the stress field. And delta sigma is the average slip that we observe within each of these three zones. And this is kind of showing it graphically here where our points are plot with this equation. So the cyan, purple, and black are the values for these three zones. And so this ratio gives you delta sigma here. And so the green dots here actually show the values for landers. And so actually it's interesting, they fall pretty close into the same ratio. Okay, so for the central zone, we get a value of about 9 megapascals. So now we know the radius of our Mohr circle, which is great. We still don't know its location in absolute stress space yet. One thing we can do also is then plot all the slip, the fault surfaces within the central zone. So if you see the points between these brackets are what's plotted right here. And I've colored it by the slip magnitude. So what you can see as you go from kind of north to south along this bend is that the slip magnitude starts to taper and decrease. And that's because these faults are becoming more poorly aligned to the stress field. So that normal stress is increasing along this transpressional bend. So I've also plotted the SH max here. That's derived from our slip vector inversion. So you can see as this bend changes orientation, the normal stresses will start to increase on these fault surfaces. And that's what we're seeing here. Okay. And so what we can then do is, now we've related this, the slip magnitude to the initial stresses, we can then start to try and constrain the frictional properties. So Valera, to answer your question, this is the original Aki equation, and we've done some work to then introduce the effect of the fault orientation with that stress drop. So specifically with the initial stresses. So that's why we have all these geometrical terms here. So we're left with this equation, which we use to estimate the dynamic and the static friction. So the static friction is built into here through these two terms, phi s, and theta s contains the static friction, and it's also contained in this I term here, which is the fault stability. I didn't write this all out because it gets very messy, but essentially what you can take away from this is that with this relation, we're left with the dynamic friction and the static friction, and we know W, C, and G from finite fault source inversions. We get the shear models from SKEC, CVM, and we know these other terms I just went over. So we can then, and then we know the displacement, we measure those with our deformation maps. So what we can do is then invert this observed fault slip for the dynamic and static friction. And so this relation basically is giving us an idea of how the fault slip should vary as a function of how well aligned a fault surface is to the stress field. And that's kind of expressed by this fault instability criterion, this quantity here, I. It gives us, it's kind of a nice compact way of expressing how well a fault is aligned to the stress field. And so that's what this I value varies from 0 to 1, where 0 is a value for a very poorly aligned fault, and 1 is a value for a very well aligned a fault that's very well aligned to the stress field. It's very close to this failure envelope here. So that's what we do next, is we invert this equation, the fault slip for the frictional parameters. So we'll start on the figure on the right. Okay, so this is showing the slip magnitude as a function of that fault stability, and I've called this by the distance along the bend. So 0 is a point along the northern part of the bend, and as you go along this bend, the colors decrease, the slip magnitude decreases, and the fault instability decreases because of that increase in the normal stress. So you can see the slip magnitude is decreasing along this bend, and as is the fault instability. And so this red line is showing our best model fit. You come out with a static friction of 0.161 and a dynamic value of 0.29, so values that are pretty reasonable. So now we know that the static friction from that equation, we can, assuming that there's no cohesion, we can then use this as our failure criterion line. We assume there's no cohesion because prior work has shown that the fault was pre-existing. One interesting feature is you can see that the fault geometry associated with the epicenter lies very close to the critical failure point right here. So now that we also plot the dynamic friction line here too, this is shows the dynamic friction. This also kind of gives an interesting idea of which faults are kind of slip within this region between the static and dynamic friction lines. And so because we now know this friction line must be tangent to the Mohr circle, we can then calculate the phi naught, or the orientation of the fault plane that's critically oriented to the stress field. That's this equation here, which is a function of the static friction. It's a value of 29 degrees. We can also calculate the initial shear stress at that critical failure point, which is about 7 megapascals, and also the critical, or the initial normal stress at that point, which is about 12 megapascals. So now that we've kind of trapped our Mohr circle, you can kind of think about it, we've kind of trapped our Mohr circle according to this failure criterion. We can calculate the confining pressure. It's a function of the initial normal stress, the radius, and 2 phi naught. This is basically this, geometrically think about this, is just this right angle triangle here. It's about 17 megapascals. We can then calculate the absolute stresses, the principal stresses, because we now know where this Mohr circle is. It must be tangent to this failure line. And so we calculate sigma 1 with P plus delta sigma, and the same for sigma 3 and sigma 2. So this gives us the absolute stress values for each of these principal stresses. And these are the values we come up with, about 20 megapascals for sigma 1 and 2. So sigma 2, we know is about 20 megapascals. We can ask, okay, so what depth of these stresses is representative of? So assuming a hydrostatic stress profile with lithostatic pore pressure, we can turn this equation around, that classical rho GH, and say, okay, what is Z given we know sigma 2? And so from that equation, we can then show that these stresses would be representative of the stresses in the top 1 or 2 kilometers in the crust. Okay, so we can then take that a little bit further and say, okay, well, these are the stresses at the surface. What about maybe what could we say was happening at seismogenic depths at the hypocenter? So here's our Mohr circle that we have, I showed before, at a depth of 1.3 kilometers, where sigma 2 is. So what we can then do is say, okay, we know the hypocenter was about 7.9 kilometers depth. That would correspond to a sigma 2 of 131 megapascals if we're calculating this at a depth of almost 8 kilometers. We can also try and get an idea, use a prior estimate of the stress drop at the hypocenter. This comes from a paper and review by Agnes Gabriel. It's a preprint online. You can read this if you want. And so from her dynamic inversion models, where she kind of like tweaks the rupture properties, the stress drop, to the observed ground motions and the fault slip from geodesy and seismic inversions, she can back out the stress drop. And so we use the stress drop value to define our new Mohr circle at depth. So I basically run that stress drop value through that stress rotation calculation again to get a new radius for a Mohr circle, which is about 50 megapascals. So that's what's shown here. And then this is our new stress tensor for that at depth. Here we're assuming that the stress tensor is the same shape, the same orientation at depth. That might not be true, but for now, this is something we're making. And it actually agrees pretty well with that static friction line. If we extrapolate that up to here, it's very close to the failure friction line. It's off by about 1 or 2 megapascals. Yeah, and so if I just make that quick correction, say, okay, well, maybe there's some uncertainty in the hypocenter depth, or in our delta sigma in the stress drop, or the stress rotation. Let's just not say for now our stress tensor is right on the failure envelope here. What are the static and the shear stress and normal stresses? We do that same calculation again, and we come up with an initial shear stress of about 47 megapascals and an initial normal stress of about 70 megapascals at the hypocenter. We can compare this to values from Fialco 2021, who he looked at the dihedral angles between seismic lineation. So he's trying to look for conjugate faults from the seismicity. From those dihedral angles, you can then estimate the static friction and the depth average shear stress. And he comes up with very similar values for the static friction. Ours is slightly higher, and our shear stresses are in good agreement. His depths are about 7 kilometers. We're looking here about 8 kilometers. And so that failure criterion and the stress tensor seems to agree pretty well with what he's shown around the Ridgecrest area, which is encouraging. So one other thing is that we have an idea of how the stress drop relates to the we have an idea of how the stress drop relates to the slip magnitude, given the fault orientation, given the deviatory stresses in the crust, and given the orientation of the ambient stress field. We can then say, okay, how does our predicted polystatic stress model compare to the observed slip along the rupture? So just comparing our the observed slip from our geodesy or image correlation maps to that predicted from our simple quasi-static model for these three zones. So the south and north, the vertical dash lines that show the extent of these three stress zones. We also calculated the stress rotations in three different stress zones. We get different, maximum shear stresses or different radiuses for a Mohr circle here. And we get a slightly lower dynamic value for the lower stress, the southern stress zone compared to the central stress zone. The northern stress zone, we don't really have enough points here to invert for the friction. We only have 7 or 8 points. So here we're just assuming that the dynamic friction is the same as that as the central zone, which may or not be true. But for the most part, this we can explain the first order variability of the slip fairly well. So one of these, the possible implication of this result is, people, a big question of geology is what are the how repeatable are slip variations along a fault? How repeatable or characteristic are they? Is it really random from event to event over multiple earthquake cycles, or is it very characteristic and repeated? So in Kling's study, looking at the a historic earthquake along the Fuyuan fault in China, he managed to resolve 5 to 6 past slip distributions, and he showed pretty good. He argued that each of these large events seemed to be pretty consistent, and so this would favor either of these two models, where the larger events are repetitive, but you have smaller events which have small amounts of displacement. And so here, what we would argue is that given the most of these large first order variations of slip are affected by the fault geometry relative to the stress field, it would be consistent with either of these two recurrence models to describe how slip varies as a function over time, assuming there's not large changes in the stresses from over earthquake cycles. But of course, there's other factors to consider that affect the variation of slip along ruptures. There's the elastic moduli, fault maturity and cementation, prior stresses. Sorry, I should have some citations here, but these are things that are widely observed, and so our quasi-static stresses can explain the first order variation, but also there's regions where at the edges of segments, fault segments, we can't explain. And so we would need to invoke other processes as well as dynamic stresses too. So yeah, just quickly on the last slide here, we looked at the Ridgecrest earthquake, which is a pretty immature fault system. We have data sets for 16 other events or 14 other events here. I think I have 16 in total now. And so one thing we can look at is how we apply this method to other more mature fault systems. So we have slip profiles for Denali, Kogachili, and Ismit, which are pretty mature fault systems. So the next thing we want to try and look at is how the friction may vary for these more mature fault systems. So are they weaker, which is something that's thought to apply to the San Andreas fault, because there's a lack of a heat flow signature, which is thought to indicate a weak fault surface. So with that, I think I'm maybe a little over, but I think I'll leave it there with the conclusions. And if you're interested, you can scan this QR code and you can read our post-print, which is archived right here, which kind of goes over what I just talked about. So with that, I think I'll leave it there and take any questions.
Awesome. We'll take questions. Eugene, go ahead.
Okay. Hi, Chris. Thanks for the great talk. I have a question on the when you're calculating the stress, like good orientation of faults and bad orientation of geometry and independent friction. I wonder if that also, does that apply to both unruptured faults, or both unruptured faults and also pre-existing faults? Does that have that constraint?
So you're asking,
so I wonder if the method works for both pristine faults and mature faults.
So newly formed faults.
Newly formed faults.
That's from stress drop to slip or something.
Right. Yeah, it should. So faults that are newly formed would likely be more aligned to the stress field, and older faults may be more poorly aligned to the stress field. And that's something that Yuri Fialko talked a bit about in that study I showed. That younger faults, because they're newly created, are typically oriented fairly well to the stress field, and older faults have been rotated over time. And he showed independently that those older faults have they have a lower static friction because they've been misoriented to the stress field.
Thank you.
And Barbara?
Yes, hi, thanks for the interesting talk. A bit complicated for me, but still. And I'm wondering, is there anything in what you do and that could indicate why a particular earthquake started rupturing from the north rather than from the south of the segment?
I mean, one thing, if I go back to the fault instability figure, is that the faults in the south are fairly poorly misaligned to the stress field. Right here. So you can see the faults in the south are
Chris, we can't see your screen. You
Oh,
stopped sharing. Yeah.
Oh no, what did I do? There we go. You can see that?
Yep.
Yeah. Yeah, so these faults in the south are more morally misaligned compared to those in the north. And so yeah, we showed that that region where the epicenter occurred is very close to rupture, where as you go further south, those faults are more poorly aligned to the stress field. But I mean, there are also factors considered. I mean, dynamic rupture models have shown that the stress changes kind of prohibited rupture too along the southern part of the fault, and that the epicenter of the main shock further north was encouraged due to there's evidence of migrating seismicity and aseismic slip too. So there's other things to consider there.
Thank you.
Kellyanne.
Hey Chris, awesome talk.
Yeah.
I'm curious, like if you had no bend in the fault, you would still have like a slip profile, and your bend represents like a pretty big portion of the fault. So I'm trying to wrap my brain about how like to deconvolve those two effects, like the effect of just slip tapering towards the end of the rupture, or at least tapering over the rupture, versus like this mapping of stress to slip. And
yeah, so that's why we tried to just limit our measurements to the central portion of the rupture. We didn't try to go too close to the terminations of the fault where you expect the faults to taper from dynamic stresses. So if our bend was located a lot closer to the fault terminations, I think that would start to be more of a problem. Like, I mean, there's also this bend here in the north here as well. There's a bend here and another significant decrease in slip, and we tried to avoid looking at that because there just could be the expected tapering of slip as it reaches that termination, which could be resulting from the dynamic stresses. But again, we can argue we can explain that with a quasi-static model. But yeah, it's not really something it's something we wanted to try and avoid. But sense. Yeah, that's a good point. I mean, you have to have a really specific scenario where you have a nice bend in the middle of the rupture, so you're confident that these are resulting from quasi-static stress changes and not dynamic stress changes, which is an assumption here.
Yeah. Thanks. That makes sense.
Hey, Chris.
Seth, go ahead.
Great talk. I just have a question. Do you have imagery for between the foreshock and that main shock that will allow you to evaluate the stresses for that foreshock, for the larger foreshock, and the stress along those fault orientations?
Yeah, the images exist. So I did correlate Planet Lab imagery, which allowed us to separate the two events, but those images are really noisy, and we can only get the 2D component of displacement, so we wouldn't be able to get slip vectors and constrain the stress state. So is your question to try and understand how the stresses may have changed as a result of the foreshock, or is it just to try and isolate the two from each other?
Yeah, I guess both. You know, how they would have changed, and may have changed the stress state leading up to the foreshock.
Yeah, it's a good question, because the foreshock intersection is with the main shock is right here. And so we were concerned a little bit about the stresses induced by the foreshock could be one reason why we have this tapering and slip. So there's the dynamic model by Julian Lozos, and then also the study I cited by Alice Agnes Gabriel. And they both show there are some stress changes along this bend, but we are starting to get further and further away from that intersection point. And they do start to become small. It's on the order of 1 or 2 megapascals, which if you look at our stress tensor, 1 or 2 megapascals would basically shift some of these points by 1 or 2 megapascals in either direction. So we wouldn't think that those stress changes would significantly change our frictional values here.
Okay, thanks.
And Alba, go ahead.
Hi, Chris. Great talk. So if the thing that really enables doing this is having a nice change in geometry on the rupture, like earthquakes like Denali or Balochistan are just essentially like one big bend. So do you envision expanding this technique to those bends, and what's missing, or is there something missing to be able to do that with your current technique?
It's a great question. Yeah, so Balocistan's like the next one we want to look at. The issue is that for this analysis to work, we need to calculate the maximum shear stress, and we get that from the stress rotations. And there's not a good aftershock catalog there, so it's difficult to do that. There is a good fault geometry, and there's a lot of good studies using INSAR and 3D optical data now that we have a good constraint on the fault geometry, but it's usually those two parameters that are the biggest hurdle. So for Denali, we don't have a good idea on the shallow fault geometry, although there's a fairly good aftershock catalog. So yeah, for Balochistan, that's kind of the main problem, is that it's a remote area, so we don't have a good aftershock catalog for those events. Hector Mine's also a nice example too. There's kind of a nice bend along there, but again, we don't have a good idea of the shallow fault geometry, and we only have high resolution aerial data. We haven't adapted the Coseismic technique to handle aerial images, so we don't have 3D data for that event. So we don't have 3D slip vectors, so that's another issue too. So also the types of imagery you have is another problem. Yeah.
Yes,
One last question. So I'm curious about the uncertainty, or that's kind of associated with what is the smallest magnitude this technique can be applied to for earthquakes?
Yeah, that's a good question. I think one thing to consider though is it's 2 parts to that question. The first part is what's the minimum amount of surface motion you can detect with these images to be able to estimate the slip vectors? And so typically a rule of thumb is that you can resolve about 1/10 of a pixel. So if your images are 10 meters like Sentinel-2, you can resolve a meter displacement. So that's kind of one issue. So like magnitude 6 events, that's going to be quite difficult with optical data. You might be able to use INSAR for that because the phase gradients might not be too high in the near field. The other thing to consider though is that in this Aki equation, or in this friction analysis, we're assuming that the dynamic friction is constant in each of these zones because we've reached that d sub c value. So you don't want to go too small where you're starting to really question this assumption that you've reached some steady state friction.
Okay, thank you.
I could ask one last question. Right, for Ridgecrest, what is striking was the almost exactly orthogonal orientation of all these secondary factors, including the foreshock, but also a lot of little ones highlighted by aftershocks, including those that Yuri looked at. Are those generally less favorably oriented, and are they systematically different in terms of their frictional strength from the trace?
Yeah, they are. I mean, I didn't look at those geometries or really at all, but looking at the orientation of the foreshock, that, well, actually, I can't say. Some of them are fairly well oriented.
Mm-hmm.
Yeah, I can't say by actually making that calculation. So it's hard for me. That's a good question. That'd be a good thing to look at. Yeah.
And Karen?
One last teeny extra. Am I like, maybe I'm missing a step, but can you do this just from like field measurements of offset? Like, could you? Like,
yeah, the issue is that, right, the issue I feel is that, I mean, first of all, I think you need to make sure you're getting the total offset across the fault rupture zone, because then if you're looking at individual fractures within the fault zone, then you're going to be subject to fault interaction within the fault zone itself, and you're not, like stress interaction or stress interaction between fractures within the fault zone, and you're not going to be sensitive to the regional stresses or the ambient stress field around the fault zone. So that's my only concern. But yeah, theoretically should be if you can get the full total slip vector.
Yeah, that's interesting.
Cool. Well, Chris, thank you again. I know it's very late there. I hope you have a good night's sleep.
Yeah.
There will be pizza and refreshments on the balcony, second floor. You'll have to come back here and join us for that another day. So thanks again, and yeah, hope to see you again soon.
All right, thank you, everyone.
Thanks
so much.
Bye.
Bye-bye.